Hey, everyone. All right, starting a little late, I think I'll dive right into it. So my name is David Borel, and I'm here to talk to you today about performance optimization in Unity for VR. VR is a particularly performance-intensive use case for Unity, and they've been very helpful and fixed a lot of things and made a lot of optimizations that you can take advantage of. And in many cases, it's just a checkbox or a dropdown. But rest assured, a lot of code went into making those things possible. So I think we should all clap a little bit for Unity's optimization in their developer support organization. So thank you. All right, so a little bit about me. I lead the portion of our SDK team that's focused on engine integration. So we work with Unity on the integration, but we're also working closely with our SDK team to implement new features for improved latency and performance, and new features like touch, where we've been heavily involved in the touch launch, which is coming up in December. This talk is going to be somewhat technical. I'm going to try to just go through it quickly, and then hopefully at the end we can have some time for questions. So yeah, I'll talk a little bit about how you can just enable VR for those 60% of the people in the room who have not actually made a VR app. Hopefully this will be enough to get you started. But really, most of the talk will be focusing on where performance bottlenecks can appear, how you can detect them and root cause them, and then what you can do about them. And then hopefully we'll have time for Q&A. So it's very easy. Out of the box, Unity has a checkbox to enable VR, and when you check it, Oculus appears. And if you're building for Android, that'll be Gear VR. If you're building for Windows, that'll be Rift. We do not have the Mac support that still exists for DK2. Actually, it is on by default. So if you install the 0501 runtime for DK2, that'll still work with Unity on Mac. Although not very well. There's a lot of judder and tearing. Not necessarily recommended. But it's good for debugging if, as many Gear VR developers do, you use Mac. You can also use Unity's out-of-the-box spatialization support. They recently added a high-quality spatialization path that uses the Oculus Spatializer plugin. It's licensed under a very permissive license, so this does not have any coupling with the Rift runtime or using Oculus hardware. You can use it with any hardware, VR or non-VR, that you want. And if you want to read our license, it's on our website, or you can ping me after the talk, and I can give you more details. It also supports Linux and other things, so it's a little bit different support matrix from our regular SDK. But what the spatializer does, it's a high-performance, high-quality head-related transfer function filter, and it also includes some room environment cues, including a room model that you can set dynamically, and early reflections. Out of the box, the early reflections and room model are turned off, and I'll get into audio optimization later. But if you just enable this, you'll get very, very good performance, and you can have well above 16 simultaneous spatialized sounds. It works pretty well, so I encourage you to tinker with that. We also have a platform SDK, which is not built into Unity. It has some of the same functionality as UNet, but it's really more focused on social. So it's kind of about rooms and like having parties of people with Oculus IDs joining an experience together. It also has voice over IP support, which I'll talk about later. We use that in the Avatar, or actually we talked about that earlier today. We use that in the Avatar SDK. And it also has peer-to-peer networking and transport and other features. OK, so once you've brought in the SDKs that you're interested in, you do have to rework your app a little bit in many cases. There's many other talks covering this in much greater depth than I will. But you do often have to think about the camera model and the way that your UI works, raycasting and things like that. You need to do all that in world space. So some rework is needed in some cases. But one of the things you really need to be conscious of is your new performance budget. Dropping frames, although it's not as severe of a consequence as it was maybe a year ago due to ATW and ASW, which I'll get into later, you still want to be generally hitting 90 frames per second. And then latency is also a concern. So if you have, for example, like volumetric rendering that has like a multiple frame, kind of settling time, you kind of want to avoid things like that because they will have noticeable latency in VR. Okay, so your targets. If you're targeting Rift, you're generally targeting a rec spec machine. So if you go to our website, there's a list of hardware specifications, and I think any place where it's ambiguous, I would assume kind of lower quality. So assume they're using a magnetic hard drive and like single channel RAM and stuff like that. But the most important thing is probably that they're probably using a 970 or greater GPU and a CPU in kind of the Haswell class. But then on Gear VR, the thing I often optimize for first is like the ancient Note 4. If it runs well on that, then it'll run well on anything since then. We also support the S6, the S7, basically all the Samsung phones since then. The Gear VR Active, the S7 Active is not supported. So if you're trying to decide which S7 to get the regular or the Edge. And Note 7 has not continued to be supported. Generally on Gear VR, you have 10x less performance than you do on a single frame of Rift rendering available to you. So that's not to say that the hardware is only 10x less powerful. We're also cutting some corners for you, rendering fewer frames per second, and fewer pixels per frame. But in general, you have about a 10x lower threshold for dropping frames. Another important concept is tracking. On Gear VR and on, if anyone here actually used a DK2 or DK1 or earlier, we had IMU-only based tracking. So that was using a gyroscope and accelerometer, which we collectively call the inertial measurement unit. And that just reports a reliable rotation reading. It does have positional data in the device, but we don't use that because it just frankly drifts far too fast to be useful to the app. So what we do in those cases is infer the position based on the rotation and a head model. So we have like an up vector and a forward vector to get from the base of your neck to your eyes, and then we assume that as the head rotates, that your eyes rotate with that. Not too important from the perspective of performance, but that's kind of the limitation that you're facing without a tracking solution. So for the Rift, we have IR cameras tracking LEDs on the headset, and it's not used as a general purpose webcam or anything like that. But you are paying a slight CPU cost for decoding those frames. And then there's also USB 2 versus USB 3. USB 2 can be slightly more CPU intensive, so be aware of that when you're running on extremely low-end hardware. If you're already CPU bound, be sure to test with USB 2. And then there's also work, as we announced at Oculus Connect, on inside-out tracking in a mobile setting. That will get more coverage in the future, but just expect a Gear VR-like use case for that. So we have a concept we talk about a lot, which is time warp, and other people call it reprojection. The specific way we do that reprojection is by shifting the image that we've rendered. So this is something we have to do quickly after the frame has been rendered, but before it's scanned out on the display. And the only, some of the techniques that are used to do reprojection are, there's some people have used height map, vertex texture fetch, and things like that. Those things have their pros and cons, but one thing that works very well is a rotational correction by shifting the image. So there have been multiple iterations of time warp. The first thing we had back over a year and a half ago was synchronous time warp, which was run implicitly by the end frame command, or basically as soon as wait for end of frame retired, Unity would start working on this. It would take the rendered image and shift it immediately on the same thread that you did the rendering on. Unfortunately, that leaves a hazard where if you don't finish rendering the frame in time, then there's a significant jump in the tracking, and it leads to a pretty jarring experience. And anyone who doesn't have asynchronous reprojection is going to run into this problem, which makes you'll have to be very mindful of performance in those scenarios because there's no forgiveness for dropping a frame. The user will immediately feel some degree of discomfort. Fortunately, we've come a long way since then. and we've introduced asynchronous time warp. What this does is essentially perform the same kind of correction at a fixed, with a hard real-time deadline. So in the system, there's a very high priority process actually that's scheduling these operations, and it'll actually preempt your rendering if you're in the middle of rendering. On different GPUs, there's different interruption granularity, but basically it'll just come in and do the reprojection before continuing. And that'll fix kind of potholes in the rendering. You still need to hit 90 frames per second on average, but this will clean up a lot of the stuff that would make users potentially uncomfortable in other situations. Okay, so at OC3, we introduced a new technique called asynchronous space warp. And this builds on top of time warp to also correct the image data itself. And the major win there is that it also deals with positional movement. But it also deals with discontinuities in your animation. So it deals differently with different types of content. So you have transparent layers may cause some slight artifacts, but none of them is anywhere near as severe as a dropped frame. So the things that work well with asynchronous space warp are like rigid body motion. If you have kind of stylized renderings, these things tend to work very well. And if you're dropping frames there, be sure to turn ASW off while you're doing performance tuning because it may not be apparent. And what it actually does, I should mention, is it always, when ASW is enabled, the app is rendering at 45 hertz, and we're upsampling to 90 hertz in that case. So the way it gets enabled is we watch the performance of your app, and if you're unable to consistently hit 90 frames per second for some period of time, we switch over to ASW until you're once again rendering in the amount of time you would need to hit 90, and then we may turn it back on. But there's a lot of low-pass filtering on that to avoid any kind of thrashing. But if you want to update the data and you have transparent layers or anything that would cause ASW artifacts, always strive to render at 90 hertz. I should also mention one more thing about ASW, that it's not necessarily an ultra quality settings enabler. It's not necessarily desirable to get a high-end PC and then render at 45 hertz and just shoot for peak quality. That may work in some cases, but you also should think about running on rec spec or min spec machines, which are kind of a new lower tier, roughly around like an AMD 480, I think is meeting rec spec. Like a 960 or so, which generally is about half as powerful as a 970. You can now essentially have a very close experience to what you had on a 970 on those lower tier devices. That's kind of the problem we're trying to solve with this. But I mean, I guess you're the developer, so you can make your own choices on that. So other techniques. So there are improvements being made in the engine to support stereo. Rendering two eyes back-to-back is quite a lot of redundant work. And Unity in 5.4 introduced single-pass stereo rendering, which consolidates a lot of the state switching. So instead of traversing the scene twice and incurring a lot of cache misses, it does one traversal of the scene, issuing draw calls to two buffers, one back-to-back in each draw call. So that creates about the same amount of overhead communicating with the graphics driver, but it does reduce the amount of, it improves the locality of the rendering. So another thing you can do is what we call instant stereo rendering, where you actually consolidate those two back-to-back draw calls into one and literally have the amount of CPU utilization communicating with the graphics driver. So this is essentially what the multi-view extension is doing on Android, which was recently implemented in Unity and may eventually appear in an alpha, but I don't have a specific time frame for it. Instant stereo rendering is also possible on PC. D3D11 has extensions that support this in various ways. The traditional ISR concept is implemented in a D3D11 extension that allows you to render to two different elements in a texture array simultaneously. And we're hoping to enable that in the near future. Then in the deep future, you could see the GPU work. So although we are consolidating the CPU work, the draw call is still producing two tasks on the GPU that could be consolidated, and that'll probably happen at some point. So never stop optimizing, basically. If you're running on Gear VR, you can always reduce your power consumption. You can get down to CPU level 0 and still reduce utilization, and it'll go into low power states more often, and then you'll further reduce your probability of an overheat. You'll reduce your battery drain. So, for example, with our Netflix application, we're able to run that at CPU level 0, and you can watch a full 3-hour movie without it running out of battery. So there are advantages to things like that, instead of having to fog up the lenses and take off the headset periodically. And on PC, it's also a win because the less time you take to render, the later we can schedule your work, and the lower the latency will be. So suppose that your app isn't performing well. How do you at least measure the performance of the app to understand where it's not performing well? Well, we have a high-level debugger. OK, here it is, the Perf HUD, which you can bring up at any time by running our debug tool and enabling it. It'll show up on top of your app in an overlay. And it'll show you this real-time graph. And it'll tell you how many compositor frames are dropping, which means if you're actually seeing compositor drop frames, that's our bug. But app drop frames would be something for you to optimize. That can be due to CPU or GPU utilization. So you're going to want to further break it down and say, how much time did I spend on the CPU versus the GPU, which that'll also tell you. And then based on which resource is the most saturated, you're going to want to take one of two courses in optimizing. Either look at the CPU load and break it down and find what's consuming the most time. And sometimes it's death by 1,000 cuts, which means that you have to kind of optimize everything and make a sea change in your CPU usage. And sometimes it's just one thing that I would call a slug, a performance bug, that you can just knock out and hopefully double your frame rate. And if you're really wise, you can throw those in at the beginning of development, and then you can fix them at the very end to make everyone extremely impressed. Just kidding. OK, so Unity's profiler is actually excellent for a lot of these use cases. It will tell you in the hierarchy view, which you can use on Android or PC, it'll tell you kind of what operations within your scripts are taking the most time, and also what within Unity is taking the most time, assuming that it's instrumented. This is something that happens on a per frame basis, so it's not going to be as helpful for like startup times or specific operations. But on a per frame basis, you can break down the timing. You can also get a sequence diagram of what happened during a frame. So in case the overall utilization was low, but you still had like bad queuing behavior, which again would probably be our bug. At least you can see it. So if you see any spikes like that, drill down. Sometimes you need to be a little bit more transparent in your code and like name things more uniquely, or like you can add your own profiler scopes in Unity that'll show up in this profiler view, and you can kind of suss out where the time is being spent. But you'll probably, in many cases, find a single thing that's spiking or 2 or 3 things, and then you can just go through them and reduce the utilization either by using fewer iterations in some loop, like a solver, or you can just pull things out or avoid GC collects. These are a lot of causes for spikes. So in addition to the low-level, it's relatively low-level hierarchical view, there's also kind of a stats window in the editor, which you would probably want to keep an eye on. We have performance targets, which I'll mention later, for both Gear VR and Rift, that you should try to stay below. I'll just tell you now, on Gear VR, it's about 100 draw calls, which is pretty low, and 100,000 vertices or triangles, whichever is lower. You can go over these, but it's going to kind of make the overall envelope tighter. So you're probably going to want to be very conscious of how many draw calls you're issuing, how many vertices and triangles. And if you're up at like 500 draw calls and 500,000 polygons, that's probably something you need to fix. So here's that sequence diagram I was telling you about, the timeline view in Unity's profiler. It's just one of the tabs when you have the profiler up. And it'll tell you throughout the frame what the CPU is doing. If there's bad queuing behavior, in many cases you can see it here. So if like the job scheduler is doing something with physics and it's waiting on something. If you see something that your app can't control, just file a bug report and we'll take a look. But I think at this point it should be pretty robust. On Android, sometimes it's a little bit hard to see exactly where your GPU time is going. There isn't always instrumentation for the graphics driver, so although on PC you get a nice detailed hierarchy breakdown of your GPU time, you don't get that on Android unless you're using like Tegra devices and some others. We're working with graphics devices with GPU vendors to improve that situation, but for the near term, kind of the instrumentation you do have is Unity's internal profiler, which will just periodically dump to logcat stats for total GPU time. If you see a large number above 16 milliseconds, you're probably running shaders that are too complex, or you may be rendering primitives that cover too many tiles and they're being duplicated many times. It depends a lot on your workload, but if it's taking over 16 milliseconds, there's probably something you need to debug there. If it's less than 16 milliseconds and you're still not hitting frame rate, let us know. If you're on PC, there's also another lower level tool for debugging the sequence of operations in a frame called RenderDoc. This is super useful. The way it works is it kind of injects itself between the graphics driver and Unity, and it'll actually intercept all the things that you ask the graphics stack to do. So it'll be able to tell you all the surfaces that you set up, all the vertex buffers and everything, and kind of the sequence of operations that you went through. And if there's like corruption or you're seeing bad results, you can often trace it down in there. The only problem with RenderDoc is that, again, you need the app running in steady state, and then you kind of capture a frame in many cases. So if there's like something happening on the first frame, actually it can catch that too. So it's a pretty powerful tool. And if RenderDoc isn't enough, or if you're seeing bad queuing behavior, for example, in the timeline view in Unity, you can also use ETW, event tracing for Windows. Event tracing for Windows is just a framework that's extremely flexible, it's extremely useful, and you can actually use multiple tools to actually interpret the data that it collects. But what it does, it's relatively non-invasive, meaning that the app will perform about the same as it did without ETW enabled. But it'll dump out a trace of standard Windows events that you can then load up in Windows Performance Analyzer, which is somewhat similar to Unity's hierarchy view. It'll generally give you kind of a top-down view of where the app spent its time. But what we use a lot, even at Oculus, is GPU view. And that'll tell you, this is probably a lesser-known graphics. How many of you have heard of GPU view before? Yeah, it's kind of unknown, and that's why I'm pointing it out. It's basically the sequence of operations across the whole system. So it'll tell you all threads, all processes, all cores, and the hardware queue for the graphics driver. It'll tell you, exactly what memory transfers are queued up, what tasks are waiting for what tasks. So here's what it looks like when you run it, and don't be scared. The layout here is there's a stack of queued up events there. So each kind of chunk of tasks there is a queue. And each time the queue changes, it's because something has been retired from the queue and has been finished. So in this case, we were debugging a hitch we were seeing. There was like some spike that was causing, we thought it was maybe a physics issue. It looks like it was actually a vertex buffer that was too big, and then it was causing like a page fault. So here we can actually see the graphics driver waiting for the request to be fulfilled, and then the GPU is waiting for that, and so then everything piles up, waiting for this one page fault. So it can be pretty surprising when you actually find out what's causing these issues. So I would assume that it's a simple problem first, or not assume, but rule out simple problems first, and then you'll often be surprised the source of your slowdown. Which leads me to another point. You probably want to write code that's simpler first. Sometimes people over-fixate on one particular optimization or possible cause of slowdown. There's lots of causes, so it's better to just make it easy to debug and then figure it out, barring any egregious architectural decisions. OK, so if you actually want to use GPU view, all you have to do is install the Windows SDK, make sure that you enable the performance analysis component, and then GPU view will be installed in there under Windows kits. We provide a script that will install a manifest with kind of the names of the events that are interesting for our SDK, so that when you run your app, you can run the script to install the manifest and start recording, and then you run the script again to stop it, and it's called OVR log. So it's actually really simple. You just run OVR log twice while your app is running, and it'll collect between the two calls. And then run GPU view to open the resulting trace. Once you're in GPU view, you can view the different events that are occurring. One of the things that I kind of use as a compass is the vsyncs. The first thing I go in and do is visualize all the vsyncs, and I'll draw big red lines through the graph and show you exactly when the display updated. They are unique for the NVIDIA and AMD direct mode drivers. So with VR, we don't use standard Windows compositing to render to the display. We use what's called IHV direct mode. So these graphics drivers have different events for their own vsyncs for that code path. So the standard Windows vsyncs are not valid for VR. But once you know where the vsyncs are and you see some frames that are taking too long to render, for example, you'll see the GPU hardware queue stacked up and then lumping over the vsync and not making the deadline. And then that's what a dropped frame looks like in GPU view. You can zoom in on that and see what were the packets waiting for. And that's usually kind of the ground truth for what to debug. So as I mentioned, you have this queue of packets, as GPU view calls them, waiting for each other. That pink one is a fence. So basically, they've submitted a bunch of operations and then a fence to make sure that they all clear before it continues. And here we see that the packets are then getting scheduled on the GPU. If you click on them, you can get a lot more metadata and kind of trace it through the system. So this is a super useful tool. Unfortunately, on Gear VR, there isn't a tool quite this low level, but there are a number of tools that you can use together to find equally or similarly low-level information. So we do provide one relatively high-level tool called OVR Monitor, which you can use to connect to your running app. And one of the design goals of OVR Monitor is to be super low, not intrusive at all. So you enable this dumping on the mobile SDK using ADB. No, actually, OVR Monitor now does it wirelessly. So all you have to do is put your Gear VR device on a wireless network, make sure the port's unblocked, and then use OVR Monitor to connect to it. And then you can enable tracing. It'll even send back the frame buffer each frame. I think it's actually down-res to conserve bandwidth, but you can see kind of exactly what's being rendered then. And your app should still run roughly at frame rate. But it'll show you all of the operations that are occurring in the VR API, and then also the throttling and CPU levels and GPU levels of the phone, and other useful information to help you triage these issues. So here's an example of a trace. This is a simple app. It's kind of like a chess game, and you can see one frame where we're beginning the frame, and then the blue bars there are the CPU work it completes, and then GPU work. I think we just have markers at the beginning and end of the GPU work, and you can kind of see whether you're GPU or CPU bound there. And also, if there's a bug in our SDK, you'll see the VR API calls taking too much time. So that can be helpful for just kind of figuring out which direction to go when debugging issues. Another useful tool is Systrace. So this is built into Android Studio. You can generate Systrace dumps, and kind of similarly to GPU view, it shows the whole system CPU utilization and kind of the operations and what they're waiting on. So yeah, in this case, it's just going to generate like plain HTML that you can zoom in on pretty conveniently. So I think in this case, I was looking at startup times. Yeah, anyway, it'll show you kind of like why is my app taking 2 seconds to start? Oh, there's some load occurring. And another more recent tool, now that the S7 is using Adreno, you can use the Snapdragon Profiler, which is very powerful. You can connect. Unfortunately, this got a little bit garbled. But it'll show you a lot of the same information that you would normally get from GPU view. So it'll kind of tell you what all the registers contain, all the performance counters, and then the current frame buffer. But it is a little bit more intrusive, and it's generally only capturing one frame at a time in depth. So it, again, needs to, like RenderDoc, you kind of need to run your app while it's in steady state and then capture a snapshot, and then you can drill in. OK, so once you've run one or more of these tools and narrowed down an issue, actually, I'll give you my forum handle after the talk, and you can follow up if you want more specific instructions on using the tools. I thought that might not be the right level to discuss these things, but we can follow up offline if you need more help. Once you've narrowed down an issue and you have kind of a sense of where the system's spending its time, how do you fix it? Well, the first thing to be mindful of is that not all performance issues are worth fixing, because only some of them are dictating the frame rate of your overall app. So you probably want to focus first on like where's the app spending 50 or more % of its time? Like why is the app actually missing the frames? It's not worth over-optimizing something that is only consuming 5% or less of your overall time and is not blocking things. That's a surprisingly unknown thing in many cases. Systems are also full of surprises. The system's seldom doing what you think it is, so it's always worth just taking a look in one of these tools and actually understanding what's going on. Our mental models are often wrong or outdated. And when you do change something, just change one thing at a time, because I've seen a lot of cases where people changed everything all at once, and then there was a new bottleneck, but they thought that it was still the same old bottleneck, and that can cost you time when debugging. OK, so suppose that you are CPU limited, especially on Gear VR, which is pretty common due to the tiled rendering architecture. And the reason for that is that a lot of the draw calls get duplicated, and sometimes geometry will be duplicated across tiles. On a non-tiled renderer, often you have far less draw call overhead. So suppose that you're draw call limited. Generally, you'll see over 100 batches in the Unity stats window here. And again, on Rift, you can go up to probably 1,000 or 1,500. And now with ASW, you can probably go higher than that. If you have something that's consuming a ton of time, try to break up your scene and remove subsets of it until you found if there's a single offender or a single group of game objects that has bad behavior, you can isolate them that way. It's kind of crude, but it works. The light mapping is pretty impactful on performance. The overall atlas size is really important, and also use the lowest precision that you can. And a lot of people render in multiple passes, which is usually not a good idea for VR. I often recommend that people use forward rendering and only try to get everything in one pass if you can. If you have an Uber shader with lots of different permutations, or if you have image effects, it's a good idea. I try to think of that as a budget. You're trying to minimize the amount that you're spending there. And in the ideal case, and sometimes you can only get away with this on Gear VR, try to single pass forward. Alpha blending is also expensive. Anything that consumes texture bandwidth. Yeah, static batching, dynamic batching are also super useful. So make sure you've got those on and that you've got materials set similarly so that Unity can batch them. Another thing you can do is just remove vertices. There's tools out there, Simplygon and others, that you can use to simplify your meshes while having roughly the same appearance. Unity has a nice LOD management system, so once you've decimated your mesh, you can plug in multiple LODs, and then when the user's closer to a mesh, it'll swap in a high-res version. It's also worth pointing out that this has a point of diminishing returns. So if you are well below 10,000 or 100,000 vertices, and you're trying to reduce the number of vertices per draw call, it may not be worth it. Below 200 or so vertices, going to 100 is not going to help. It might literally take exactly the same amount of time. Also, texture bandwidth, although we weren't talking about that, you can reduce texture bandwidth by using higher levels in the image pyramid for mapping. So Those not familiar with mip mapping, you have like progressively lower resolution versions of the texture that it'll fall back to in certain situations, mainly based on the texture derivative. So if you set Unity's LOD bias higher, no, it's actually lower. The lower you set Unity's LOD bias, the lower it'll look in the mip map hierarchy, and so then the less texture bandwidth you'll consume. But of course, this shouldn't be set automatically. I would recommend having your artists, try to hit the lowest quality level that still looks good. We also provide OVR overlay for retaining sharp text, which I'll get into a little bit later. So when you degrade texture quality, you can still keep certain things sharp. So there's other things you can do to reduce texture bandwidth. One is to avoid excessive anti-aliasing or anisotropic filtering. That'll do a lot of extra texture lookups that it doesn't need to do. Keep your working set under 128 megabytes. And then we found that the best image quality to performance trade-off is typically found with ASTC, but you often need to fine-tune the parameters. Using ETC2 is not really recommended in Unity 5.4 because PVR text tool can have extremely slow load times, but it's also, we found, a little bit less flexible. So ASTC, generally really good performance, very good image quality. And also, when the textures are rendered to the eye buffers, as most content in Unity is, you're probably going to want to have the base resolution for those textures be 1K by 1K. If you have like 8K textures, it's going to go above 128 megabyte working set, and you're going to probably have a lot of issues. And also try to have shaders that avoid like raycasting in shaders that have like extremely divergent memory accesses. Because even though you're accessing the same number of texels, if they're very far apart or unpredictable within the texture, that can cause slowdown. I think we already talked about all of this. The number of lights often strongly correlates with the amount of per pixel bandwidth that you get. You have to spend that much time per light in many cases. If you're rendering, if you're using deferred, you pay a high upfront cost, but then you can scale the number of lights faster. That's not necessarily worth the trade-off on VR because deferred typically works better with a small number of pixels and a high number of effects per pixel. Whereas VR typically has extremely high resolution eye buffers in a very short time per frame. So in general, I try to avoid deferred rendering, but there are apps that have been successful with it, so use your own judgment. Another lever you have is automatic resolution adjustment. So Unity 5.4 now has render viewport scale, which if anyone who here has adjusted VR.render scale? Okay, so we've all done that, or a lot of us. At 1.0, and it's kind of a magic number, but at 1.0 on Gear VR, that corresponds to a 1K by 1K texture. And that's because that's the recommended eye buffer resolution. It's not like the panel resolution like it is on Rift. At 1.0 on Rift, the center of the screen has 1 texel per screen pixel. So it's kind of the point of diminishing returns for image quality. That's a very high number, and in many cases you can drop that safely without harming your application and save a lot of performance. On Gear VR, similarly, you can crank that up to 1.5 and get arguably better image quality, but you're going to be dropping a lot of frames. So again, that's a tool you have. Render viewport scale, on the other hand, so render scale, every time you change it, has to reallocate the eye buffers because they have a new resolution. Render viewport scale will keep the eye buffers at the resolution they previously were based on the render scale, but they'll render to a subrect of them. So then you can quickly change the render scale if you're responding to bad performance, or if you know that you're jumping into a scene that's going to be texture bandwidth or pixel shader bound. So you can quickly ramp it down. We do have a feature in OVR Manager and the Oculus utilities that will automatically govern the render viewport scale based on the current frame rate. And you can set the upper and lower bounds for that. And the way that works is that it will automatically allocate setting render scale to the high value, and then it'll use viewport scaling to reach to the low value if performance drops. But by default, it'll try to target the high value. It'll go as high as it can without dropping frames. Another thing is OVR overlay. So we have a compositor in our SDK, both on mobile and PC, that can take textures and literally raycast them to the display instead of performing distortion correction on the eye buffer. And that avoids double sampling. If you directly sample with high quality filtering, you can essentially be panel limited. When we say panel limited, I mean like with the lens and the actual screen, rather than being limited by our SDK rendering approach. So if you have your UI rendered to an OVR overlay, you can keep the text and the important bits crisp while you scale down the resolution of things like this house, which I don't think anyone cares that much about, more so than dropping frames. Overlays are also useful for cursors because only overlays can bypass time warp. If you set them to headlocked, and in Unity, the way you do that is by making them a descendant of the camera, then they will automatically move immediately with the head and not be time warped, and so there'll be no wiggle. So if you have like a reticle or something, it'll quickly respond to user head motion. So here's the API that Unity 5.4 offers, and I hope nobody's too offended by the indentation issue there. We recommend a particular MSAA level for each hardware target. So on PC, we typically recommend 2x, and on Adreno, we recommend 2x, but on Mali, 4x seems to be the point, kind of the knee in the curve for quality and performance. There's also a monoscopic mode, so if you're doing 360 video and you don't need the content to be different between the two eyes, it'll essentially set the IPT to 0, which makes it look like everything's infinitely far away, but then you'll literally pay half the cost because it's only rendering one view per frame. And we also recently released a sample that has a different approach to monoscopic, where you can render the background monoscopic and then shift the images to get parallax of a split plane where you transition, and then stuff in front of them can be rendered in stereo. So then if you have stuff like a faraway castle and like a nearby card game, you can render the card game twice and render the castle once. Also in audio typically shows up as a CPU bottleneck. But with our plain HRTF filter, you can just use, I think the sky's the limit on number of sources. You can probably go up to 32 or 64. I guess that's not the sky, but it's pretty high. Once you turn on early reflections, you probably want to keep it well below 16. I've seen cases where people with 5, you generally pay like 5% per source, depending on how far away the room reflection walls are. Because the decay can be longer for further away walls. And again, Unity has a nice built-in profiler for audio system utilization, and since all of the audio spatialization is being kind of managed by Unity, it does have a lot of profiler info about that. You're typically not going to run into that many bottlenecks with our platform SDK. The VoIP system is probably the most resource intensive. Try to keep it below 4 users. OK, that concludes the talk. We have other resources. So I'd encourage you to read our developer blog. Actually, there's a number of other articles about improving performance. And if you're confused or if you just want some help, please never hesitate to reach out on our forums. So you can just go to forums.oculus.com. And then there's a Unity area that I and a number of other people watch closely. So let's hand it over to questions now. Does anybody have any questions?
Are you publishing your slides?
Yes. I think Unity is going to publish them all in the same place. And I will probably also put them on the Oculus website. Any other questions?
Yeah, the pixel light guideline for 1 pixel light, is that mostly because light sets a separate pass? I mean, what if you had something like the lab renderer and you actually had a single pass but multiple lights in the same shader? Would that still work well?
That's a good point. Yeah, if you have a single pass that can accommodate multiple lights, that would work fine as well. Yeah, so if you're literally using the lab renderer, that should work fine. And it's up to you as well. If you make your per light cost low, obviously that'll scale better.
Do you have any good recommendations for real-time shadows? What I've known is basically super low poly proxy for shadows.
Yeah, unfortunately, real-time shadows, at least the default implementation, can be slow. Cascaded shadow maps seems like a really good approach. It kind of depends on the implementation. The filtering settings can influence your bandwidth costs a lot. I have seen apps successfully use Unity's built-in CSM, so just be very careful about the quality level. I think we have a Tuscany sample that we put on our website that set them kind of the way that I would recommend. Yes, regarding the physics system. So the iteration count and the allowed penetration can both be pretty significant. It's going to spend the most time on the CPU if you have a lot of rigid bodies with complex colliders all close together. So avoid that because it solves them on kind of an island basis. So if you have only simple proxy meshes for physics, reduce the poly count to on the order of tens to low hundreds, and then try to limit the number of objects that are all near each other and especially interpenetrating, because once they're interpenetrating, then there's a constraint solver that kicks in, and that's expensive as well. There's a lot more to talk about with physics tuning. I think there's actually a Unite talk going on that covers that in a little bit more detail, but there's also a nice write-up on Unity's website on the Learn area. Sorry, you guys. Yeah.
Can you just talk a little bit more about the split monoscopic rendering you're talking about?
Sure, yeah. So the idea there is that you have two cameras. One of them is using a faraway near plane, and one of them is using a closer far plane, and those abut. And then the faraway stuff is rendered in monoscopic, and then since the image would have the wrong parallax there, it would look like it was infinitely far away. We have to shift it apart to make it match the parallax of the split plane. So it's just a couple of pixels shift. And if you set the plane far enough away, it's kind of an insignificant shift. But the point is that we make sure that they kind of composite properly. You may see, if you draw a straight line that crosses that split plane, what you would see is kind of a slight bend. But we originally, when we set out to do it, thought that it would not be a win due to texture bandwidth cost because you have to read back the monoscopic texture and composite it with the stereo view. But it turned out to be a big win in a lot of cases. But it's very content dependent.
And that's unique to the Oculus platform?
Our sample could easily be used with other headsets, yeah.
How well these things can be applied to other devices as well, for example,
So as far as I know, I think Valve has implemented reprojection. I'm not sure whether they have ATL. I'm not really sure about the details of their SDK, but all the Unity level stuff is pretty much directly applicable. The ETW workflows are all transferable. Systrace, Snapdragon Profiler, all those things would also be applicable to Google. But yeah, I mean, our SDK tries to do a lot to help you hit frame rate, but yeah, I think the techniques presented here would be applicable to both.
The number of vertices and triangles you can draw for Rift, is it specific to some graphics card, or it's
Yes. Yeah, so all of these guidelines are assuming a rec spec machine for Rift. Many people have more powerful machines, and you may want to have like an ultra quality setting for those people. But this is kind of what you would need in order to hit frame rate, especially if you're running on a min-spec machine with ASW enabled. So yeah, if you go to the Oculus developer blog, again, we have the specific requirements for a rec spec machine. And if you double the GPU power, you can kind of assume that the texture bandwidth could double as well. Okay, thank you for your time.